Welcome to the VHDL Design and Modeling of Digital Systems course, Functions. Here's the syntax for a function. Pure or impure, followed by the keyword function, followed by the function name, then a optional parameter interface list, and a function actually returns something to the caller. And here's where we define the data type and the name of what's returned. Followed by the subprogram declarative part, begin keyword, and the sequential statements that are within the function. At some point in the function, it must execute a return statement. Something else I wanted to say about pure as well is the keyword pure. If there's no pure or impure in front of function, then pure is assumed. An impure function need not return the same value each time it is called with the same parameters. The function that we talked about before called now, which returns the time at the present runtime, will not return the same value. There are no parameters passed to it. So now when it's defined, when it's declared as an impure function. The parameter interface list syntax is similar to that of a procedure, except that we do not have signal, constant, and variable. We only have signal and constant. Also, as far as modes are concerned, we only have mode of type in. We also can pre-initialize it to a static expression, just as we can with the procedural parameter interface list. Here's an example of a function called limit. We have 3 parameters being passed into the function, and 1 parameter, or 1 return. Value, min, and max are integers being passed into the function, and the function returns an integer. Begin, and it checks to see if value is greater than max, return max, value less than min, return min, otherwise return value. Now notice that regardless of the execution path, at least one of these, or only one of these 3 return statements will be called, but a return statement must be called by the time it hits the last line of the function declaration, which is end. A few things I want to point out as well. All parameters defined in a subprogram need not have a corresponding association during the subprogram call. This is true for both procedures and functions. Subprogram overloading is used to implement different subprograms that have the same name but are passed different parameter types. We could do the same thing here, where instead of integers we could say if they were instead positives or naturals or something such as. Functions and procedures both are visible from the end of their declaration to the end of the corresponding statement part. A subprogram may have 1 or 0 or more parameters, and a function must execute a return statement in order to pass the result back to the caller. If we want to be able to construct data types that contain numerical values, we have to have a way to define how numeric operators are, how these operations are performed on these user-defined data types. if we define a data type called unsigned word and define it as 16 bits, we need a way to be able to add them together. So we provide a function called function double quote plus end double quote to perform the addition. When we add op1 to op2 and place the result in op3, the plus function declared in the architecture declarative part is called. This function works its way from the least significant bit to the most significant bit, performing the summation. If the carry bit is set afterwards, an overflow assertion is reported. This example shows a simple case where a specific data type of a fixed size is shown. If other operations are needed, then those functions need to be defined as well. While the IEEE library contains functions that perform these operations for us, it's important to know how they are implemented. So far, when we've talked about signal assignments, we've only performed singular signal assignments. We also need a way to be able to drive from multiple sources the same signal. That's what the resolution function is. A resolution function is used to calculate the final value of a signal which is driven by multiple sources. The data type std_ulogic is defined in the IEEE library package declaration of package std_logic_1164, and these values here that you see the data type or the type declaration std_ulogic, and it's an enumerated data type. And as we talked about enumerated data types before, the first one is of note because when we define an object of that type and we do not initialize it, it takes on the value of the leftmost enumerated value, in this case u for uninitialized. The next one is x for forcing unknown, 0 forcing 0, 1 forcing 1, Z high impedance, W weak unknown, L weak 0, H weak 1, and a dash for don't care. Now, before we were living in a nice world where we only had bits that only had we only had to worry about two different values, 0 and 1. Here, though, we're introducing a couple different concepts. One is a possible don't know or uninitialized high impedance, but also forcing function as opposed to weak function. What we're trying to describe here is strength of the signal. These values allow us to model real-world concepts like pull-up resistors, pull-down resistors, high impedance state, and also be able to implement open collector drivers. Here we're creating and supporting subtype standard std_logic, standard logic, is resolved of std_ulogic. Here we're defining a type of or a table of standard logic, which is a two-dimensional array of standard ulogic. Now, if you take a look at the rows and the columns, if we wanted to find out how two different signals fared, or what they would result in if they were connected to the same point, two outputs to the same point, if we connected, say, U for unknown and or uninitialized and X for unknown, we would end up with a U in unknown. We would look at the column, first column, which is U, and the first or a second row, which is x, and look at the intersection, see that that's a u. Now if we wanted to find out any other value here, we can just check, the row and the column. Now on the next slide there's a function which basically uses this table to determine one or more drivers, how they would result. Here we've got the function declaration resolved that will basically be our resolution function for our std underline logic. The way the resolution function works is basically is passed a unconstrained array or vector, std underline ulogic underline vector. Each of the signals that are assigned to a single point are passed to this function, so that the function can determine what the result is from the multiple drivers. A couple things I want to call to your attention here is like the variable result of data type standard ulogic, and it's pre-initialized to the weakest state, namely high impedance. And it also does a special case check where if there's only one signal assigned, then return that value's or that signal's value basically in that one. That's the length of it. Now, if there's more than one signal or more than one driver to that one signal, then we execute this loop. We basically search through our resolution table, two at a time basically, assigning the result into result. And we use this two-dimensional table to determine, two or more signals that are driven, or not signals, two or more outputs that are driven to the same signal. And this function resolves what the final outcome of that or those assignments will be. Here's some example signal assignments. We have basically three signals of standard logic, op1, op2, and op3. In the first pair we see op1 is assigned two drivers concurrently. One is of state high impedance and one is weak 1. Now if we take a look at our two-dimensional table and we map out where those two intersect, the result is weak 1. High impedance and a weak pull-up, it's intuitive that they result in 1. Op2 is assigned two different drivers. One is called forcing 1, which is a strong 1, and op2 is also assigned by another output called weak 0. So we have a strong 1 assigned to the same signal as weak 0, and the result, as you'd expect, is a forcing 1. Also, op3, if we have two signals or two forcing functions, one's forcing 0, one's forcing 1, both are the same strength, so one cannot overcome the other, so the result is basically forcing unknown.